Hi, I'm Tate Williams. I'm in section W42, and this is my lab report for Lab 2 on projectile motion. So to begin, projectile motion is the motion of an object once it has been released initially and it travels through air. For our experiment, we are using a paper ball to track this projectile motion. We are recording it and putting it into the tracker program, and we are using that in the closed script program to determine its properties of motion. So first, the video was taken of the ball being thrown. It was put into tracker. It was we calibrated using a meter stick that was in frame in the video. Then point mass selection was used in tracker to determine the object's position uh, and create a table using its x and y components. Then using that data set, we can determine velocity and acceleration, and then we can use that with Newton's second law to find the proportion or the coefficient or constant of proportionality for our drag force by setting the force of gravity and drag both accommodated for equal to our net force, which we know we have an acceleration at an instant and we have the mass of the ball, and then we can solve for b. So then we can account for b in the closed script program for our net force calculations, and that will affect the ball's motion. Here's the experimental data. I've attached the uh, output. As you can see, you can't see the two additional vectors of gravity and drag because they were so small that they are covered by the ball. Here's a comparison of the different data sets' trajectories. As you can see, there's some obvious deviation here, likely due to drag force because the drag one is the most far off. So with the ball reach terminal velocity, returning to our graph, with drag, it does appear like the velocity begins to become constant at some point. It doesn't seem like the position, the rate of change of the rate of change in position is changing very much. So we can reasonably assume that in that simulation, at some point it is reaching terminal velocity because the force of drag is going to cancel out the force of gravity because they will be equal and opposite as shown in the picture. Now, let's consider a situation in which we throw it directly upward with the same speed. Would it take less or more time? It would actually take more time because speed is the magnitude of velocity, and in our experimental data, the initial velocity in the x direction was greater than the initial velocity in the y direction. So if we take the magnitude of that vector and throw it just only in the y direction, it will take longer to come down because our initial velocity is just that much greater, and the force of gravity is the main thing altering the motion. So here's our potential sources of error and our percent error. Without drag is 18.82%, which is not as bad, but it's not good. We need below 5, but it's somewhat vaguely representing the data. And with drag is extremely far off, more than like it's less than half of our actual experimental value. So let's explore the source of error. It could possibly be the camera angle of the video that was put into tracker, but this was hopefully accounted for because you can set the calibration stick at an angle and we matched it up with the ruler or with the meter stick in the video. The tracker point mass selection could have caused some deviance because if it's not exactly accurate, it can mess up the experimental data a little bit. Some programming errors with the GlowScript program could have resulted in the graphs not representing and the data not representing what it needed to be and accurately if it were produced with accurate calculations in the programming. And obviously the inaccuracy of the drag force, which is probably due to complications with either the GlowScript programming being inaccurate or the calculation used to determine the coefficient of or the constant of proportionality for drag to be incorrect.